now we'll hear about what the prospects would be if we actually have temperature superconductors, and I guess some of them are already prospects without temperature superconductors. We are looking forward to Teresa push to talk about superconducting materials and the application.
Thank you very much. So yes, so the organizers asked me to talk a bit about superconducting materials and applications, and therefore it will not be applications at room temperatures because at this moment we don't have the materials for these, but maybe in some years. But I will mostly concentrate on applications of high currents, okay, and therefore the materials for high current superconductors. So the outline will be, I will talk about what I said, superconducting materials property and the requirements for high current applications, and I will concentrate then on the practical superconducting materials, which would be the niobium-15, helium-based or HTS cuprates. I will talk on the conductors and nanocomposites that allows us to go to high fields. Also about the present situation of these materials, which is if we are not cost effective, it's very difficult to get into the market, and therefore what are the ideas there. And finally I will end up with the present situation of applications of superconductors for high current applications. So, as you know, superconductors can be a solution for many range of magnetic fields, but I would say for very low fields, a superconducting sensor with interference phenomena. But I will concentrate on the superconducting wires, which means that at high fields and therefore high field applications. So what do we need for superconducting material to be good for a high current application? So we need a critical current, of course, as high as possible. We need a critical temperature, a critical current as high as possible. A critical current as function of magnetic field, okay, that is high as possible, and that means that we need also high pinning forces. We need a type 2 superconductor with high reversibility line. We need low thermal fluctuations. We need low anisotropic materials so that we are able to wind them without having to think on which direction is the magnetic field being applied to the material. We need materials which can be industrialized and made in a scalable process with high throughput processes, with low cost, and of course easy to wind and integrate into devices. So as you can imagine, there are no materials which fulfill all these requirements, but there has to be a compromise between ones and the others, and we see then which are the good ones. Well, as you know from the early times with bare single elements and that were discovered superconductivity, then we have the niobium phases, which are one of the main used superconducting materials nowadays as low temperature superconductors with standard BCS theory being applied. Then they were discovered the cuprates, okay, which gave a great chance to go to applications, and I will stay here for some time later. It was discovered the magnesium diboride, as you know, that is also a material which is being used, or has been very much worked to get into applications, which in fact is also explained with as a lutetium material. Then the iron-based, which also for some time there has already been a lot of work, and we will see that they are advancing in this. And of course we are hoping for getting high materials with higher TCs. We'll see where we get in TC. But that is not enough, as I said. It's not only TC, it has to be the critical field. In fact, it has to be the reversibility line for applications. So the reversibility line is the line which is below HC2. This is the case of YBCO, the cuprate, so this should be HC2. This is the reversibility line, which defines the area below which the critical current density is higher than 0, and above which is 0, and therefore for applications, at the end, the important line is the reversibility line. And as you see here, TC and the reversibility line do not match, and therefore not all materials which have high TC have high reversibility lines, and there is where the first compromise that we have to take. And we see here the low TC, the magnesium diboride, the iron-based, and the cuprates. In fact, from all these materials that you have seen up to now, there are only these ones which are the ones that have been allowed to be making wires of it and therefore being able to do applications of it. So we have the niobium tine and niobium-13 as low temperature superconductors, and we have the magnesium diborite and the iron-based, which were more recently discovered, and then we have the oxides. The cuprates, so the bismuth phases, and then the YBCO, which at the moment is the one which is able to go to higher magnetic fields. So I just want to briefly, I just want only to briefly discuss about iron-based niobium-13, and then I will spend my extending in cuprates, because these are the three materials that nowadays, still for applications, a strong effort is being devoted to really reinforce the material, to improve the properties. And one can think, why is niobium-13, which is already 50 years in the market, still a problem for applications? So why do we still want to improve this material? And mainly is because in a niobium-13, which in fact the application is a multifilamentary wire, where we have maybe 10,000 filaments of niobium-13, the main difficulty is that still 50% of the material is not used as superconductor. And the point is that this is because to generate the niobium-13, you have to get the thin core, which has to diffuse through a kappa matrix into the niobium, and then generate the niobium-13. And that is a complex method, a complex material science. And in fact, what it has been shown is that in fact the grain size of the niobium-13, which is being generated, is the one which at the end determines how much current we can pass through, because it is the grain boundaries which are in fact being the pinning centers in this material. So there is now a lot of effort in order to enable more tin into the niobium-13 to get higher density of the material being niobium-13, but also narrower grains so that we can have much more grain boundaries and therefore increase the pinning force. And this has been seen that, for example, by just adding 1% in atomic percent of zirconia into the niobium, they're able to double more than double the pinning force of this material. And this in fact is now a lot of effort being done, because this is the material which is it's supposed to be implemented in the upgrade of the LHC. So a lot of effort has been put, a lot of money has been put to really improve the properties of the niobium-13. In the case of the niobium-based, it's known that there are many phases, that there are many interesting physics. It has been able to do single crystals, thin films, but it was really a problem to do wires. And nowadays also with the 1 to 2 phase, it's possible to do wires. It's possible to do wires with critical currents which are very high. So they are already in the range of 10 to the 5 at 4.2 kelvins, and therefore they are even getting better values than the niobium-tin material. So at this moment, for example, here this is in China, in the Electrical Engineering Center for Applied Superconductivity. They already have been able to get a 100-meter wire of this iron-based and with critical currents, in this case 10 to the 4th, at 4.2 kelvins and 10 Tesla. So maybe in the future we can see iron-based. And what I want to stay longer is on the cuprates, because in fact the cuprates are the ones which, in fact, YBCO is the one which is covering the larger surface of the JC, BC, and TC area. And we want to see here what is the situation now. So we see that YBCO, which at the beginning was meant to be a superconductor for high temperatures, nitrogen temperatures, is nowadays also thought for low temperatures, because we can go beyond 20, 30 Teslas for applications at 4.2 Kelvin. So, well, I think that I don't have to go through that. HTS is a non-conventional superconductor. I think you have been discussing this quite a lot along during this week. But just to remind that YBCO in particular, or HTS cuprates in particular, are not fulfilling the ideal requirements I put at the beginning, because it's certainly a very highly anisotropic material. It depends. It's not easy to fabricate it. It depends a lot on the carrier concentration. It has a high TC, but it has a reversibility line which has a lot of thermal fluctuations with vortices. So anyhow, still like this, we are able to use it. And well, I would say that, of course, what is meant now is to see what can we know more about this material as regards the mechanisms and see if we can really understand the physics. But beyond this, the people has continued fabricating these materials and understanding how to use this material to put it in applications. And the main problem of this material is that it's fragile, it's a ceramic, it's anisotropic because it's a laminar, and therefore it's complicated to put it into wire. As you know, the copper oxide planes are the ones which conduct the superconductivity. However, then we have all the blocks, which are called as reservoir, charge reservoir blocks, which are able to dope properly these copper oxide planes. And that means that if we are trying to pass current in this direction or this direction, that will be very different, and therefore this material is very anisotropic. In fact, if we look at the anisotropy of the different materials, we see that niobium-10, niobium-15, even magnesium diboride, even iron-based are quite low in anisotropy, but when we go to PUIG rates, we go to very high anisotropies, which then makes difficulties on the applications. And of course, YBCO is still from the PUIG rates the one which lowers anisotropy. This would be the anisotropy in the normal state, but that also transforms to the anisotropy in the superconducting state, so that if we pass current along the AB planes, we can pass a lot of current, but if we have to try to pass current along the Z-axis, that goes very small. And therefore, that means that these kind of materials, these high anisotropic materials, we cannot just produce them in a granular material, we have to do thin films. So we have to do epitaxial growth. And therefore, if we want to do wires and we don't want to do kilometer length, we have to do thin film technology on kilometer length, which is where materials had to be strongly improved and a lot of effort being done. In fact, the idea at the end is to put these materials in the form of superconductors. That means that we have a metallic substrate, thin substrate, on top of which we put some buffer layers in order to match the substrate to the superconducting layer. Then we put the superconducting layer on top, and then silver or copper protection. So that means that we have to do all this multi-layer technology for thin film in kilometer length. And it has been now already 25 years working on being able to prepare these materials. And at this moment, we already can say that we have several companies able to produce 500 amps in 1 centimeter with tape at 77 Kelvin, in lenses of 500 meters, 1 kilometer. But if we go at 4.2 Kelvin and 20 Tesla, we can pass over 1,000 amps. So clearly this material at the end, 25 years later, could really demonstrate that it was a high current material. Of course, one of the main problems is that the substrate, because we have to grow it epitaxial, okay, the substrate somehow has to be textured. However, this is not easy, and what it was demonstrated is that there are several techniques which are able to start with a polycrystalline substrate and then get it into texture, and that is the sputtering technique. This is called IBAF. This ion bombarding with a sputtering the ions of a buffer layer, which then also another ion beam is sent to the material, being rejecting the orientations that you don't want, so that at the end you are able to grow an epitaxial layer on top of a polycrystalline layer. And then on top of this epitaxial layer, you have to grow the other buffer layers and the YBCO, all things epitaxial, okay, with good lattice mismatch. The other possibility is what is called rabbits, which means that you start with a nickel or nickel-based material and do a thermomechanical process of rolling and annealing, so that at the end you end up the nickel will be textured, and then on top of this nickel you have to put the buffer layers and then the superconductor. At the end, at this moment, we have many companies which are able to produce these superconductors. Each one are using different substrates, different buffers, different superconducting layers or cuprate layers. But at the end, the point is that this is feasible. It is not only done by one single company, it can be done by several of them. And we have companies in Europe, we have companies in Japan, in US, and Korea, and in China. And this is just installations of these companies, just to give you a flavor that in fact this is possible. This is Bruker, which is at this moment able to get 1200 amps at 4.2 Kelvin and 20 Tesla in pieces of 600 meters. This is that was by pulse laser deposition. This is MOCVD, metal organic chemical vapor deposition in US with superpower, also able to get over 1,200,000 amps at 4.2 or 500 amps at 77. And then this is also in Germany, the Nano. These are all using an all chemical solution deposition, which is a very low cost technique, able to get also over 300 amps at 77 Kelvin. So the point is that, well, if we want to go to high fields, we need to deal with vortices, and therefore we need to deal with vortex matter. And again, HTS is not the ideal material, because even though we have a very large mixed state, we have this reversibility line, which in fact does not enable us to work in this area. But also, the interplay between defects and vortices has been quite complex matter to study, and how each of the defects is affecting the pinning of vortex is important, because in fact, because we are in very low coherence lengths, the defects of the order of few nanometers are the ones which are pinning centers. Okay, so in the case of the niobium-3 tin, we had grain boundaries as pinning centers. Here, grain boundaries have to be avoided, and in fact, the pinning centers are nanometric defects. And to control nanometric defects is not so easy, but also because we have high anisotropy, because we also have then also high thermal activation energies, because we are working at high temperatures, this also difficult that vortices have to be pinned properly. And that also tells us that, of course, we have many different types of defects that can pin vortices with different dimensions. We can have oxygen vacancies at point defects, or we can have dislocations in 1D defects, or we can pin vortices in planes like twin boundaries, or we can pin vortices in 3D defects like secondary phases. But altogether, the difficulty is that at the end, when you produce a material, you have all of them there, and you have to know which of them is the one you want to promote, depending on which magnetic field and which temperature you want to work with. And for that, therefore, you need to have some models which is able to separate these different contributions when you do actually a measurement. Okay, and in this we have also been contributing quite a lot. At the end, we are able to define that different defects with different dimensions are able to contribute in different ways into the critical current density, and therefore, depending on where you want to work, you are going to emphasize these ones or these ones. So these ones for low temperature are very good. These ones or these ones are very good for high temperature applications. At the end, what we see is that if we look at the critical current density as function of the magnetic field, we see that this is the niobium type, the niobium-3 tin at 4.2 Kelvin. This is the YBCO Cori conductor at 77. But if we are able to properly put pinning centers, we can go from this line to this line. And if we now go with this kind of defects to low temperatures, and we control the pinning landscape engineering, we see that at 4.2 Kelvin we are also able to get YBCO at these values, which are really much higher than the low temperature superconductors. And that's why at this moment many of the applications are also thinking on YBCO at low temperatures as a high field conductor. So how the best at the end, the best artificial pinning center in YBCO has been what is called nanocomposite, and this is to be able to put a nanometric secondary phase into the material, which it's not reacting with the superconducting phase, and which can be spontaneously segregated during growth, and that can have a nanometric size so that they can pin the nanometric vortices. So for techniques like pulse laser deposition or MOCVD, it has been possible to get nanorods. So these are nanoparticles which are aligned in the form of nanorods, which are able to pin vortices very easily if you put them any field in the direction of these rods. In the case of chemical solution deposition, we have been able to put nanoparticles into the material, which are also good pinning centers. In fact, if we look at the pinning force of these nanocomposites, we see that from the pristine values we can really go to very high values of pinning force, which in fact at 77 are able to double the pinning force value that you have in the niobium tie at 4.2 Kelvin. And these are different ways of producing these nanocomposites. If you go to 4.2 Kelvin there, you can see that you can even get pinning forces which go beyond 1.7 teganewtons per cubic meter, which is more than 100 times what you get at 4.2 Kelvin for the niobium tie. Okay? So clearly there's a lot of interest for these materials at high temperature but also at low temperature. Now, in the case that you want to produce these rods, that is done with processes where when you deposit the YBCO material, you are also growing the YBCO material. Okay, so this is the case of MOCVD or PID. And when you want to grow the nanocomposite, you deposit both phases at the same time. One has to segregate from the other, and it has, because they grow at the same time, you can benefit from the lattice mismatch, and you can end up with a strain which allows to organize these nanoparticles in the form of rods. Okay, so there is an interaction between the growth of the YBCO and the growth of the nanoparticles. In this case, you can play with the growth rate. In the case of pulse laser deposition, you can play with the laser frequency, for example, or the power of the laser, with temperature, with the composition of the second phase. We also can, and then you can end up with rods which are very short or rods which are very long that go through the full layer. You can end up with rods which a bit get out of the z-axis, or they are very strictly aligned. And what you see that when you calculate, when you measure critical currents, when you go next in the same direction as the rod, you see that the critical current is extremely increased because vortices are pinned in the rods. This would be without rods, this would be with rods. And you can work with different phases, barium zirconate, barium tin, phases which in fact have to really not be able to react with the YBCO phase. There has also been a lot of effort understanding how is the the strain between the rod and the YBCO matrix, and realizing how much this semi-coherent interface is playing a role also as pinning centers. In fact, this strain is the one which at the end allows to orient all these nanoparticles in the form of a rod, instead of having them all distributed. And there has been elastic models really able to corroborate the experiments, which are able to also determine which is the phase, which is the size of the nanorod that will be formed, depending on what material you are using. And at this moment, this is a work from the University of Houston. They are able to really get rods surface spontaneously segregated of only 3-4 nanometers with very high densities, which are the ones who have been able to demonstrate this 1.2 teganewtons per cubic meter. If you go to other growth processes, like the one which first we deposit the precursor phase and then we grow the YBCO, so that is that we first deposit and then grow. This would be the case of chemical solution deposition, for example. In that case, when you want to form a nanocomposite, you also deposit both phases, but the nanoparticles will segregate before into the intermediate phase, and therefore they will be formed. And then when YBCO will form, it will encounter the nanoparticles. It will encapsulate these nanoparticles, and therefore these nanoparticles will not be epitaxially grown. So we have randomly oriented nanoparticles in a YBCO epitaxial matrix. In this case, for example, in the chemical solution deposition, we have a solution we have to deposit. Then this solution is a metal organic solution. We want to get rid of all the organic because at the end we have to end up only with the yttrium, barium and copper. This is done at 500 degrees or so, which is called the pyrolysis, and then we go to the crystalline YBCO as a second process at higher temperatures. So you deposit, you have a gel, you have to decompose this gel, you end up with nanoparticles of yttrium oxide, copper oxide, barium fluoride in this case, and afterwards you are putting it in another furnace, in another higher temperatures, and then in the phase diagram where YBCO will be likely to epitaxially grow, and then you get YBCO with the nanoparticles segregated. In this case, we also see that if we compare the sample without nanoparticles with the sample with nanoparticles, we have much higher currents. Also, at much higher fields, we have higher currents. In fact, I want you also to concentrate that we call this edge star to the place where this plateau of JC starts to decrease, because this edge star somehow is representative of when the vortices will be, all the vortices will be pinning defects, okay? So we will not have a collective behavior of vortices, and therefore it can be emulated as something like a density of pinning centers. So if we have higher number of pinning centers, this edge star is expected to go higher, okay? And this is what we see, in fact, if we compare a non-nanocomposite with a nanocomposite at any of the temperatures, here or here or here and here. And again, we see that the pinning forces of these CSD nanocomposites also increase a lot when compared to the standard YBCO without nanocomposite or also with a niobium type. Now, in this case, what we in fact see is that these random nanoparticles generate a lot of defects into the matrix of the YBCO. In fact, what we see is that the system doesn't like to have these random nanoparticles in the epitaxial layer, and therefore generates additional intergrowths. And these are these black lines that we see here. These are that instead of having one copper oxide chain in the structure of the YBCO, we do have two. So this should be only one layer of copper oxide, and we see that we have two layers of copper oxide. This layer is like you see here, this blue thing, okay? So these are intergrowths. These yellow balls would emulate the nanoparticles. These intergrowths are these blue areas, which are called stacking folds, or 248 intergrowth. And at the end, at the surrounding of this intergrowth with the YBCO matrix, which would be all this, we see that there's a lot of strain which is also accumulated. And what we have been able to see is that in fact the pinning force is increasing with this strain, which can be in fact evaluated by XRD. So here what we have claimed is that in fact the strain we have accumulated into these areas, what it's doing in fact, the strain is at the end is lattice displacements. What can be done, what it's been doing is that when you have that the copper oxide orbitals are tensile strain, then there is no overlap, and therefore you are able to get no pair condensation in that region, and therefore if this is done in nanometric areas localized all over the material, this then can be nanometric pinning centers. And therefore this is a way to explain why this nanostrain, which is localized in a nanometric area at all the surroundings, is able to have a proportional linear relationship with the pinning force. In fact, if we calculate from different areas, from different samples with different nanocomposites, the density of these stacking folds and the length of these stacking folds, and we do statistics on this from the TEM images, and we assume then we calculate what is this area which is surrounding where the strain is, okay? Then we can see that in fact, this area, which is the density of this dislocation, which is the one which is surrounding the stacking fold, is proportional to this edge star value that I mentioned before. So we can confirm that in fact, at these areas, which are the ones surrounding these stacking folds, so these green areas are the ones which in fact, where the strain is accumulated and is where in fact they act as good pinning centers. Now, more recently, we have been able to decrease the size of these nanoparticles. As maybe I didn't mention it before, but when you spontaneously segregate these nanoparticles in the material, the nanoparticles end up with dimensions of the order of 15, 20, 25 nanometers. This for high TC is too large in order to be a pinning center, because it should be in the nanometric scale. However, what we have seen is that it's not the nanoparticle itself, but all these defects and all this strain which is generated around these nanoparticles, due to these nanoparticles, the ones which are doing the pinning sites. But if we are able to encapsulate nanoparticles which are a range of 5, 6, 10 nanometers, then maybe the nanoparticles also would contribute as pinning centers. And to do this, what we have done is to prepare first the nanoparticles and then throw them into the solution of the YBCO, having a colloidal solution, and then grow the material. In this case, the nanoparticles do not have to spontaneously segregate during growth, but they are already there on the face that we want with the size that we want. Of course, then you have to avoid that these nanoparticles coarsen. And this has also taken quite a lot of effort, but doing very fast heating processes, we are able to encapsulate small nanoparticles. And in this case, what we see, that then the edge start. Now we have, for example, this is the pristine sample. This is when we have a nanocomposite, so the nanostrain increases. This would be a pristine sample at these high heating rates, because we have then a lot of defects generating just by the high heating rate. But this would be the same high heating rate with the nanoparticles. So what we see here is that we can have samples with the same nanostrain, but higher edge start, which in fact confirm that if these samples which have very small nanoparticles, these nanoparticles might be contributing to this edge star. So there are additional defects that not only this nanostrain, but also the particles themselves. And this can be proposed because these nanoparticles now are in the range of 2 times or 3 times the coherence length. Now, what do we want if we want to get this material into applications? Of course, I have been discussing that we have to have them good in performance, okay? So nanocomposites would be one of the ideas that have been really worked a lot to have high performance. We have to pass high currents, that means thick films, because it's not the critical current density what we want, is the current, and therefore thicker films, higher currents. Of course, we can decrease the substrate thickness, and therefore when we wind, we will use less area because we encapsulate. But also, the main difficulty nowadays is that they are too expensive. Too expensive because, of course, this is a multi-layer technology, so a thin film technology, which has to compete with mechanical drawing and ways of producing the low temperature superconductors. So in order to do them cheaper, of course, one way is to do high fast growth processes. And from what I have just said now, we have different ways of producing these films. In fact, these are the different growth mechanisms for YBCO crystallization. So in many of the cases, like pulse laser deposition or MOCVD, what you are doing is growing the YBCO from a vapor phase. And if you grow from a vapor phase, the growth rates are in the range of few nanometers. If you do a lot of effort, in some cases, some companies have been able to get into 10 nanometers, that still can grow the YBCO even though these rods are a bit distorted. But just because from a vapor phase you cannot go much higher. If you grow from a CSD, from chemical solution deposition, after the decomposition of the organic, after the pyrolysis, you end up with these nanoparticles, yttrium oxide, copper oxide, and so on. And then from this solid, you have to go to another solid, the YBCO. And this is really a low process. It's a solid-solid reaction of the order of 1 nanometer per second. If you are able to grow from liquids, from a high-temperature supersaturated liquid, this is the way you grow crystals from, if you want to grow a single crystal, okay? If you have a liquid from which you can grow the crystal, that, of course, can then be much higher growth rates, because from a growth from a liquid to a solid, this can be very fast because atomic diffusion in the liquid is very high. So systems like a hybrid liquid phase epitaxy where they deposit first a liquid of barium and copper and then they through yttrium later, okay, they can grow much faster. So what we proposed in our case was to use the CSD advantages and the liquid advantages and try to define a new process which we have called transient liquid assisted growth that allows us to grow after the pyrolysis from these nanoparticles to the YBCO through a transient liquid. Okay, and I will just be showing. And this we have been able to demonstrate that we can grow then at 100 nanometers per second, which is 100 times higher than what we had with CSD, but with a low-cost process of chemical solution deposition as compared to pulse laser deposition or other vacuum techniques. So, in fact, the idea here is that we will have a solution. Now, the initial precursors will be different. We will have the same pyrolysis. We end up with nanoparticles. Now, we will have one of the nanoparticles which will be barium carbonate. And then we will go to this region of the phase diagram where it is where the YBCO can grow. But we will do it in a way that we will be able to first form a liquid of barium copper before the YBCO can grow. And then, when this liquid is formed, the yttrium oxide nanoparticles will diffuse in the liquid and will be able to grow. That's why we call it transient liquid, because this transient liquid phase is not the stable equilibrium phase in this diagram. But we are able to produce it if we go at very fast heating labs. And we have been able to demonstrate this in the synchrotron within C2. Maybe I can. So here, oh, and now of course we don't see it. No. Well, anyhow, the situation is this is a theta to theta scan where you can see that how the different phases are reacting, and at the end, very fast, you get the peak of the YBCO. In fact, this is the integration of this signal, and what you can see is that we can grow YBCO at 100 nanometers per second. And these experiments at the synchrotron were done through emulating this process, acquiring images every 100 nanometers per second. But we have also been able to see that this process is compatible with nanocomposites. This is quite important, but it also at the beginning was quite surprising, because you are growing 300 nanometers in 1 to 3 seconds, okay? It's 300 nanometers are grown, 1, 2, 3 are grown, 300 nanometers, and therefore, are we going to be able to encapsulate these particles, or are all these particles going to be pushed out of the liquid? Are they, all these nanoparticles are going to segregate and deposit onto the substrate? So at the end, what we have been able to see is that it's not. We are able to get nanocomposite with quite nice, short, small nanoparticles with this process. That also, we can see that we can get higher performances with the nanoparticles. In fact, we see also that we generate a lot of stacking force, all this intergrowth that I mentioned before. So we have nanoparticles, small nanoparticles, plus also the nanostrain that we had induced by this intergrowth. And we also have been able to see that the H star, it depends on the nanostrain, but also for the same nanostrain, we do have higher H stars. That means that also the small nanoparticles are contributing to this process, so that we can really get all the knowledge and all the benefits that we had for the standard CSD process in this very fast, ultra-high transient liquid assisted growth. We also have been able now to demonstrate that this process is compatible with a metallic tape, so with all the conductor structure, that we can grow YBCO epitaxial on top of the has the loyal and all the buffer layers that we have in the Corey conductor before depositing the YBCO, and that there is no interfacial reactivity between any of the layers and also not on the YBCO. And now this has been awarded with a proof of concept ERC project in order to demonstrate the technology viability of this process. So now I want to spend some time on applications. I would say that, of course, superconducting systems are more compact, less weight, higher magnetic field, but large electromagnetic stresses, okay? And therefore, and we have to take into account that all superconducting materials are strain sensitive except the niobium type, okay? So this is also something that has to be taken into account when we want to make a device. So we have applications at high temperatures and low fields, which would be mainly for energy application, cables, for current limiters, transformers. We have applications at medium fields and medium temperatures, which could be electrical motors, generators, so for airplanes, for navigation, for wind generators. And then we have applications at ultra-high fields and low temperatures, which would be for accelerators, fusion, or NMR. In fact, we have to think that in this case, NMR resolution is proportional to the B minus 2 square, fusion power is proportional to B to the fourth, and the beam energy in an accelerator is proportional to B, and that means that if we can really increase the magnetic field on these applications, we really win a lot on the potential of what we want. Of course, that means that if instead of using all these with low temperature superconductors, we can change it to high temperature superconductors, we will benefit a lot because with, as I showed, with YBCO we can get much higher fields than with low temperature superconductors. But of course also we have to take into account that these materials are still expensive, as I said, so we need to invest time in order to produce material at lower cost. The detection of the quench is very complicated in high tissue superconductors because the IV curve is very sharp, with an N value very sharp, and therefore it's very close. It's very complicated to stop a quench, and also they are anisotropic and so on. Even though, like this, we can say that at this moment it's already 3 years since there have been many cables demonstrated in superconducting and HTS in particular. Okay. This is what the last example, one example that I want to show because this is right now already installed in Essen in Germany in the grid for the last 3 years. It is in a substation giving light to energy to the population there. It was initially 100 kilovolts net superstation that now it has been replaced with for a 10 kilovolt cable of 1 kilometer, and therefore you can really work at much lower voltage because you are able to increase the current. Okay, so and now there has been a project in Munich which also has been just approved that will also work with HTS cable. First they demonstrate 200 meters, and if they are successful then they have a 12 kilometer cable to be installed in Munich. A fault current limiter is interesting. Fault current limiter is a system which is able to benefit from the superconducting transition. So superconductor in the superconducting state has no resistance. Superconductor, when it goes to the normal state, has a resistance, and therefore we can put a superconductor in a network, and if it's in the superconducting state we don't see anything, but if there is a fault, current fault, then the critical current will be a shift, and therefore we will put an impedance into the network, and therefore we will increase the resistance, therefore we will decrease the current of the network. Right? So this is what you see here, for example. So this is current versus time. Without, when there is a current fault, without the fault current limiter, you have very high currents, which at the end is what destroys the equipment that you have in the network. If you have a fault current limiter, superconducting fault current limiter, as soon as the current is increased, this impedance avoids that the current keeps in, and therefore it decreases the current. So this is interesting to be able to do parallel meshing in the network. Is interesting also for when now is being considered the possibility to have generation of energy in one place and distribution in another place. So you need very long distances that have to work with DC cables, which is therefore better to use less energy than with AC cables, but also they have to be protected as fault current limiters. And here, for example, we are now in a consortium which is called FastGrid in the EU, which is able to demonstrate that we can grow one cable, being also fault current limiter of 1 kiloamp at 50 kilovolts. And here, there are still now main issues in the fault current limiter is not to quench the material in a homogeneous way. Because as I said, when you quench this material, the thermal conductivity is very small of HTS, and therefore you quench here, but you don't propagate, and therefore you can really break the material. However, there are means to really do that this quench propagation can be much faster, and this is the ideas and materials on this project. Now, electrical planes. Yes, it's true that nowadays there's a lot of push to go to electrical planes for the environment and for the energy protection. And when we go to electrical planes, again, superconductivity can make a role because you can do motors which are and generators which are much compact, okay, and can also benefit from a hybrid situation where the hydrogen could be also one of the fuels of the electrical plane. So at this moment, Airbus and NASA and also Boeing is having some projects working with HTS to be superconducting motors and generators. And there's also some projects in EU working in this case. So what it seems at this moment is that a hybrid situation, that there will be the initial proportion with just a standard combustion plus, but then all the other generators and all the other motors that you have in the plane would be electrical motors. And in the electrical, there could be also the superconducting motors. In wind generators, that is also another possibility. In fact, when we want to go to 10 megawatts, it's a bit complicated to go with the standard technology. Here you can see how much you can win in weight and in volume. And there has been also a project in EU demonstrating a 3 megawatt superconducting wind turbine. And we also worked with Gamesa in order to demonstrate that we can get one initial standard generator of Gamesa, of which is about 0.5 megawatts, and transform it to 2 megawatts if we change the stator, conventional stator with a superconducting stator. And now there's a second phase, which would be to change the rotor also to superconducting rotor, and that would enable us to go to 5 megawatts generator. And then fusion. Fusion, of course, as you know, is one of the paradigms for future energy. And at this moment, ITER is the one which is being constructed in Cadarache. There are an immense amount of superconductors in ITER, as you know. They are all niobium-ti and niobium-13. ITER is planned at this moment to be finished by 2025. And then there is DEMO. DEMO is not planned to be, so ITER is science-driven. DEMO is planned to be industry technology-driven, but it's not planned to be an electricity production system, but to enable the technology, and then it should be on. In fact, DEMO in Europe is planned to start, so to be constructed by 2054, but there are other demos in Korea, in China, and Japan, some of them much earlier in time, others in not. But for example, now Italy, the government of Italy has also financed the DTT fusion project for these years, which in fact is a small ITER in order to demonstrate some parts of the ITER which are still not clear how it have to be done. And this is just an image of the situation at this moment of ITER in Cadarache. So really a lot of effort and a lot of money placed there. So hopefully we can get electricity out of fusion. First we can get fusion and then electricity out of fusion. But what I wanted also to let you know is that since just 2-3 years ago, there has been a lot of, a couple of initiatives on doing compact fusion, and this started as an MIT study in the fusion department, and they decided that, of course, instead of doing it with low TC, we do it with HTS. Then we can really make it more compact, we can get much higher magnetic field, and therefore we can have much higher fusion power. And from that study, there has been now a company, which is being a spin-off company, which is Commonwealth, which has really raised an immense amount of money, and which is trying to build this SPARC, which is a small, affordable, reliable, compact fusion reactor. But also in UK, there is Tokamak Energy, which is also another company which just has been founded 2-3 years ago, which has also raised a lot of investors' money, who is also going to this spherical tokamak. So the idea here is that the shape of the ether, it's changed in a way that it's more compact. It is spherical instead of being D-shaped, and which can benefit, it must benefit from the HTS, because they need to get into 20 Tesla HTS magnets. In magnets, there has been now demonstrated, for example, this in Tallahassee, we have 32 Tesla magnets because of the DC, because of the LTS plus HTS. So the idea here is always that you use niobium 10, niobium 13, and then the HTS, and each one is summing the magnetic field. So they have been demonstrated that they have this 32. Also in Korea, they could demonstrate a 26.4 all HTS, this one. Also in Japan, 25 Tesla with the niobium 13, niobium 10, and gadolinium BCO. And the latest news in the Nature now is that Tallahassee has been able to get a compact 45 Tesla DC magnet with the HTS. So this is also going on. And in NMR also, as you know, if you want to really go into life science, chemistry, and higher, you need to go to higher and higher frequencies. Higher frequencies, as I said before, it means higher magnetic fields. So at this moment, Bruker has been able to go to 25.9 Tesla, with also the sum of LTS plus HTS, which means, yes, to 25.9 Tesla, which means 1.1 gigahertz. Okay, up to 1 gigahertz you can do all with LTC, so low temperature superconductors. If you want to go to beyond 1 gigahertz, there's no way to go beyond unless you also put HTS. And at this moment they have demonstrated the 1.1. They are now developing the 1.2, and also in Japan they are developing the 1.3 gigahertz, which also would be a summation of LTS plus HTS. And in MRI also, of course, the conventional MRI that we get in all the hospitals, this one is around 1.5 Tesla. This is niobium type. HTS is now opening the possibility of MRI open gap, so that you don't have to go into a tunnel, but you can really don't feel the closed environment. But also there has been demonstrated already a 3 Tesla MRI with HTS to really go beyond the 1.5. This is in Toshiba. But also beyond the 1.5, if you want to go to really understand the neurosystem, you need to go to very high magnetic fields. And for that, there are also at this moment all LTS, but there are already several projects ongoing where they have demonstrated an MRI at 9.4 Tesla, an MRI at 11.7 Tesla, and there's a project now for 17 Tesla, okay, to able to evaluate Alzheimer's, Parkinson's disease, etc. And just to finish, for the high energy physics, as you know, LHC is only possible with superconductors. LHC is all built at this moment of niobium type. There is the upgrade of LHC, high Lumi, in fact, is now being upgraded in the next year and a half, where they change few niobium type dipoles for niobium 13 dipoles. That allows them to have some space to put the collimators in order to concentrate the beam, and therefore able to have high luminosity. But after the high luminosity, they have the high energy, which means to substitute almost all the niobium type by niobium 13, and that allows them to go to higher energies. But also all the detectors are also based on superconductors. And then there is the Future Circular Collider study, which is the one, this is the LHC, so this is the possibility to build a 100-kilometer ring, which would be able to go up to the 10 tega-electron volts energy, okay, which is still, of course, to be decided because it's an international collaboration, but all the study is working. And in that case, there are also, of course, thousands of tons of superconductors. There's a possibility that some dipoles could be HTS2, but still to be ongoing. But I just want to mention also that superconductivity in accelerators can also be in another place, and that is that in the beam, when you have the proton beams which are circulating, okay, there is a lot of synchrotron radiation which is being generated because you are circulating charged particles, okay? And all this radiation is generated very close to the dipoles, okay? So this synchrotron radiation then is damaging the dipoles and the magnets. And therefore, in order to screen this, they put some beam screen. These are the tubes where the protons will circulate through, and these tubes are made of stainless steel to avoid this synchrotron radiation to touch the magnets. However, the problem is that when you go to FCC, the energy associated to the synchrotron radiation, because the energy of the beam will be so high, it's so huge that they have to, they cannot just cover with copper this beam screen in order to ensure that there will be no fluctuation of the magnetic field. And here is why we propose that in that case we could use a superconductor, a high-TC superconductor, a Cori conductor, which we would cover the interior of this beam screen, and that would ensure that the surface resistance inside would be low enough so that all the charged particles would be not influenced by the fluctuation of the magnetic field due to the synchrotron radiation. And we have been able to demonstrate that yes, that in fact we can be at the conditions that they want to work much better than copper, because they want to work at FCC with a beam screen at 50 Kelvin, because if they work like they do now in LHC at 1.2 Kelvin, they would need just a power plant to just fit the electricity of the FCC. So HTS also has other opportunities in other applications which are not only doing big magnets. So this is the conclusions. I would say that superconducting materials are an impressive nest of new knowledge, as you have seen also during this week, but also for applications, that despite all the initial difficulties in HTS, we have succeeded in manufacturing kilometer length materials with applications. The nanocomposites have really been the clue and the key to really get into high field applications. But we need low-cost, fast-growth manufacturing processes, which allows us also now to get these materials into market at much lower cost. And that in fact, this is a winning materials story thanks to the effort of all the different backgrounds. Otherwise, all this I have just told you, it was impossible just being done by only engineers, only physicists, or only chemists. So we need them all. Thank you very much.
Yeah, thank you for giving us a glimpse of what the opportunities are for medium temperature superconductors. Hopefully it motivates everyone. So student and postdoc questions first.
Oh,
come on.
Okay, just a politician question. So if you want to make a kilometer-long cable, right, with YCBCO, you need to cool it down. So is that something?
So sorry, can you?
You want to make a kilometer-long cable of YVCO, you need to cool it down throughout the whole length. So is that something that? How does that cost compare with the other costs of manufacturing and stuff?
Yeah. So if you compare how much costs a cable, or superconducting cable, or a standard cable, okay, it's clear that superconducting cable costs more. However, this is not thought to change all the cabling, but to change cables in certain places. So you have to, for example, think also on the cost of the civil work. So, for example, in an underground cable, you have to do all the civil work. However, at this moment, when you have already the civil work done, you just get one cable out, a standard conventional cable, you put the superconductor, you have 5 times more power with the superconductor, and you don't have any civil road, for example. Okay? Or if you want to put it in a motorway where you don't need to screen the electromagnetic radiation, or so there are places where in fact the cost is already quite good. And in fact the project in Munich, this is paid by a company, so it's not public, and it is the cost effective at the end is because they already have all the cabling done, so all the tunnel is done. They just want to get more power, and therefore they just get the one out, they put this one in, and this costs them less than just drilling holes and drilling tunnels to the Munich city to get more power in the conventional system.
So even with nitrogen cooling included?
Yeah, nitrogen is just, it's quite cheap. Liquid nitrogen costs the same as a Coke. So this is cheap, and nowadays you can really pump liquid nitrogen in a way that you don't lose.
Like a closed cycle?
It's all circulating.
Okay.
Good. More questions? Yeah.
How complicated is it to join these cables? Because I think you mentioned that the longest cables that are manufactured are 500 meters.
Yeah, so what I just showed is the tape, right? Now from the tape you have to go to the cable, right? And sometimes what means this is that this tape has to be winded in tape, okay? But it's true that the pieces at this moment are in the range of maximum 1 kilometer, so then you have to have joints, okay? Because this tape starts with stainless steel, and then they have all the buffer layers, superconductor, the silver and the copper, so you can just join copper with copper. Now, how much do you lose in these joints? Okay, so at this moment, the joints they are less than in the range of 0.5 nano-ohms. So really, there has been a lot of effort really to decreasing these joints, and therefore this is not really a big deal. Still, there is some effort on trying to do superconducting joints too. In some of the applications, like for example in NMR, where these nano-ohm joints are still a bit too high.
Yeah.
So you have said that here in Munich, so they are going to do this test with 200 meters. So there is already this SN cable working. So do they have to do this test because it's a different infrastructure?
It's a different company who pays. So let's say that they have a first stage that they say, okay, try the 200 meters. I see that you are able to do it, and then you go on. In Essen, the tape will be from Teva. This is a German company, which is a different provider than the one that they used in Essen, which in fact I think it was still Visco. So yeah, but I would say that what they are going to test with these 200 nanometers is that they are able to produce and that the cable is working, and then it's just to go to 12 kilometers.
Yep. Good.
All the nanorods and everything you presented was with some sort of oxide, and so I'm curious as to the choice of material to make the nanorods. You might get different functionality if you had a metallic.
Yeah, this is one of the main difficulties with YBCO or these cool grades is that there are many elements which are able to enter into the structure, and therefore they substitute either copper or and luckily most of them which substitute, they decrease properties. So you have to avoid any magnetic material, you have to avoid most of the metallic materials. So the ones that are here being used are zirconia, tin, tantalum, which are materials which are not able to enter into the structure. But also there have to be materials which are able to segregate properly and in the form of nanometric forms. So there has been a lot of materials being studied, but at the end the ones which work most are these perovskite oxides, which I showed here. Ideally you also would like to have an insulator if you want to have core pinning, for example, okay? But and there have been people trying to put magnetic rods also, which would not influence, but at this moment they all decrease TC.
More questions? I wonder on these MRI scanners, you mentioned they were planning to build now 17 Tesla MRI scanners. Is it at some point not healthy anymore to go into them? Because I think you remember.
Yeah, no, I think, well, at this here, I think the point is that they want to do first studies on animals, okay? But they more and more see that they can really get electrical signals analysis if they go to higher and higher magnetic fields.
And the resolution pretty.
And the resolution also. Okay? So I suppose that we will not be exposed to a 17 Tesla, but let's say that from the perspective of understanding and they put mice, that is poor animals, they are always struggled everywhere, and they put them disease, and then they are able to study.
Good. If there are no more questions, I think let's thank Teresa and all the people.